Okay, do you have any questions before we start about the homework? The homework is due this Monday, so you have a couple of days left. So you should be finishing up your coding and start testing soon, because you are going to also submit a report with your homework. So you should start as soon as possible if you haven't done so. Also, the videos of our lectures, they have been put on the web, the first 3 of them, and they're putting it on the web as the time goes on. So they're at this OpenCourseWare address, OpenCourseWare website, ocw.netu.edu.tr. So if you have missed some lectures, you can go ahead and watch the missed ones. And that's all the announcements I'm going to make. Are there any other questions? Yeah, sure. Yeah, so the question is, can we make certain assumptions about the test cases that you're going to try on our to test our program? Actually, those test cases are only the sequences that are going to be tested. So, for example, you don't need to use dynamic memory managed allocation. I mean, for example, you can make some certain assumptions about the sequence lengths. The maximum length is going to be, for example, 1,000, or I don't know. I have generated the sequences artificially. These are not real sequences, okay? They are generated artificially, but I generated them with writing a certain generator program with certain parameters. And I'm not going to test your programs with other test sequences. These are going to be the only sequences that your program is going to be tested on. So you can make any assumptions about the sequences you can if it's going to ease your programming. Yes? Yeah, I answered also that question on the news group. The question is if there are more than one optimum alignments, if the best alignments is more than one, you only need to report one of them. You don't need to report all the optimal alignments. It's not, just reporting one of the optimal alignments is enough. Then there was another question that you asked on the news group, which was, oh yeah, the output it doesn't matter actually. The output you are going to put in your report, whatever your program is not going to be tested by using a black box test. So you can have, anyway, your program is up to you, okay? You can provide any output. You can either write your output into a file or on the command prompt. In both cases, it's very easy to redirect either to a file or to print the contents of the file, so it doesn't really matter. Okay. Any other questions about the homework? No? So let's continue. We were talking about last time the suffix tree, which is a tree of suffixes for a given string. And the suffix tree does not always exist if suffix is a prefix of another suffix. So that was the example. If you have a string like XXXX, and in this situation like this, XABXA, this is another example. The suffix XA, so XA here is a suffix, and it's actually a prefix of another suffix, which is this, XABXA. So in such cases, we will not be able to draw a suffix tree which satisfy all these conditions. I mean that we have here. Okay, every internal. So we will violate, for example, the fact that all the suffixes are denoted by leaf nodes. Here, this suffix will not have a leaf node associated with it, because since it's part of this longer suffix, that pad is going to end in the middle, and we are not going to have a leaf node special for this suffix. To solve this problem, we said we can put a terminal character at the end of a string, which does not exist in our alphabet. So that's the solution. Okay, the terminal character $ is used. $ is not a DNA sequence or a protein. It's not an amino acid. It's not a nucleotide. Therefore, we can safely use it for DNA or protein sequences. We can safely use this dollar sign, which is not in our alphabet, and put that at the end of our string. And this way, this suffix is going to be $. Therefore, it's not going to be the prefix anymore, because this dollar cannot appear anywhere in the somewhere in the string. It cannot appear. It only appears at the end, and therefore no suffix can be a prefix of any other suffix. So this is how we avoid this situation. And this $, is going to have a special leaf for it. If we for the same XAB, XAC, this is the suffix tree for XAB, XAC. As you can see, this XA, previously it ended here, which was not a leaf node, it was an intermediate node, sorry. Okay. So, but now it's not an intermediate node anymore because of this dollar symbol. $, suffix can have a leaf of its own. And dollar suffix also is the last suffix. So we increase our string size by 1, and that's the final suffix tree. Now let's let's talk about an algorithm to construct this suffix tree. This is a quadratic running time algorithm, which means that it takes, if your sequence is of length n, it's going to take O(n) square complexity, asymptotic complexity, to construct the suffix tree. And the construction is pretty straightforward, actually. It's an iterative process in which we try to add each suffix one by one to a tree, to an intermediate tree. We start, so we start with the root, okay? First we have a root in our tree, and we put suffix leaf numbered 1, okay, the first suffix. Okay, a leaf number 1. The first suffix is the string itself. So, and the edge is labeled with the complete string with this dollar terminal symbol. Okay, so we start with this tree. So this is also a tree with a root and a single leaf node, and the edge is labeled with the complete string. Okay, we start with this complete. This is our initial tree, and we add to this tree one by one, starting from we add the second suffix, third suffix, fourth suffix, until we get to this suffix. There are this many plus 1 suffixes. Okay, the length of your string S plus 1. That 1 plus 1 comes from this dollar terminal symbol at the end. So we have this many suffixes, and by using this many steps, by adding a suffix each time to this tree, we'll be able to construct the final suffix tree. So how do we proceed afterwards? So what is when we are entering the second suffix, what do we do? What we do is this. We follow the path from the root for this, for a specific suffix, for an intermediate suffix that we are trying to add. We try to follow the path from the root by matching the characters of this new suffix on the edge labels on this path, okay, to the edge labels on this path. If, for example, let's consider this XAB, $, example, XAB, $. The first thing we do is add this, the first suffix is XAB, $. We add it, so this is the first step, the easiest step. Now the second step is to add AB, XA, $. So this is our second suffix, AB, XA, $. And we try to follow the path from the root to and by matching the characters of this suffix one by one, starting from the root. So we have an A, and this edge label starts with an, let me write it like this. This is the edge label starts from X, so it's XAB, XA, $. This is our edge label. And the first character in this edge label is X, which is a mismatch with our new suffix ABX, $. So we have a mismatch at that point when we try to match the labels. So if we have a mismatch here at that point, we can safely add a new leaf having this AB, XA, $, label. because we do not violate the rule that here, what we try to do is we don't want to violate the rule that the edges that leave an intermediate node has to start with different letters. Okay, therefore, and since this starts with A, this starts with X, this starts with A, we have no problem there. We can have our suffix completely as a new suffix. So if you actually have a string with all different letters, okay, for example, A, B, C, D, E, F, G, H, the suffix tree would be a tree with depth 1. Okay, it's going to be a very simple tree. Each suffix as a separate leaf and no intermediate nodes at all. Okay, each suffix can be directly connected to the root node if you have a string of A, B, C, D, E, F, G, H, with all different characters in the string. The problem occurs, so we will not also have the problem for the third suffix, which is BXA dollar. Okay, this is our third suffix, BXA dollar. It can be added easily as the third suffix because when we try to match the letters of the suffix starting from the root, we get a mismatch initially, so we can do that. But more formally, the algorithm can be described like this. To insert the ith suffix, we follow the path from the root, matching the character of this ith suffix until the first mismatch at character J, okay? And so, as I said, which is bound to happen. Why is it bound to happen? Why we are sure that such a mismatch is going to occur? When we are inserting the ith suffix, we try to match its characters one by one, following from the root, and we are sure, we know for sure that a mismatch is going to happen at some place. How can we be sure about that? Yes? Yes, exactly, because we made sure that no suffix is a prefix of another one. If we get all matches, it means it's a prefix, okay? It means that no suffix is a prefix of another one means that we should have some mismatch somewhere when we're inserting this suffix, we should have a mismatch somewhere. It means that if you can match all the characters on a path, it means that a suffix is a prefix of another one. So you should get a mismatch somewhere so that the suffix you're inserting is not a prefix. Okay? The fact that the suffix you're inserting is not a prefix ensures that there must be a mismatch at some point. I mean, that mismatch may occur at the last character, that $sign. Okay? We are going to see that will happen in this case. For this XA, when we are trying to insert XA, that mismatch is going to occur at the $sign. But it's going to occur on this path. So let's label that mismatch character as KJ, the jth character. Okay? And there can be two possible cases, this mismatch. This mismatch can happen at the middle of an edge, okay? Because when we are following a path from the root, we are also matching the characters one by one on an edge label. So a mismatch may occur in the middle of an edge. So XA is matching, for example, but B and dollar is a mismatch. We may have a mismatch in the middle of an edge, or we may have a mismatch at the beginning of a node. This mismatch either can occur at the first, at a node, meaning that no characters leaving that node starts with the character you're looking for. So you can stop your search at a node or in the middle of an edge. And these are the two cases, A and B. If the matching cannot continue from a node, if there's a mismatch at node, we denote that node by W. What we are going to do is we are going to add a new child to that node W, starting from using the strings from J to N. We are going to insert this substring as J to N as a new child node to root W, to node W. If a mismatch occurs at the middle of an edge, we need to split that edge. if we have a mismatch in the middle of an edge, we split that edge label into two, and we are going to add a new intermediate node at that point. In the second case, we need to add a new node, intermediate node. However, in the first case, all we do is just add this remaining characters of the suffix you are inserting as a new child to that node W. Okay, this is the algorithm continued. If the mismatch occurs at the middle of an edge, what we do is we name this edge label. The previous edge label was SU up until V. Okay, this one shows that edge labels does not need to be prefixes or suffixes. An edge label can be any intermediate substring. Okay, this mismatch may have occurred somewhere in the middle of this tree, in which the edge label is just an arbitrary substring of the original string. So this notation just shows that it's a substring from the u'd character to the v'd character. Okay, so let the label of that edge be this A1 to AL. If the mismatch occurs at character AK, then we create a new node W. So we create a new intermediate node named W and replace E by two edges with the first. So we replace this one. So we insert a new node W here, and we split these. The match part is going to be this edge label, and the mismatch, starting from the mismatch character, we have a new edge label going out of this node W. Okay, so this is the one that was, this Kate character was the mismatch character on this previous edge label from U to V. And then after that point, since in both cases we have the same node W, and we add this new mismatch part as a new child to this node W. So I'm going to, this formal description has no ambiguity. If you read this formal description of the algorithm in detail, you are going to see it covers all the cases during insertion. So it's a self-sufficient description of the construction algorithm. Now let's do an example construction for XAB XA dollar. So let's do it whether we are going to get the same tree as this one. So let's do XAB XA dollar insertion. We already did the first three steps. XAB XA dollar. Okay, this is suffix 1, suffix 2, and suffix 3. Actually, let's follow the formal algorithm. So this is the first thing we inserted. Then when we are inserting a second suffix, which is ABXA dollar, we have a mismatch at a node. Okay, at this root node, we have a mismatch. This X does not match with, so this root node does not have any child which starts with the character A. Okay, we do not have any edge coming out of which starts with character A. So we have a mismatch. We cannot, when we are inserting this ABXA dollar, we cannot follow any path from this node. So we have a mismatch at this point. And if we have a mismatch at a node, we simply add this as a new child from this mismatch part. We add it as a new child here. We do the same thing. The third step is very similar to the second step, BXA dollar. Now, the fourth step, when we are trying to insert XA dollar, let's see how we do that. We start following XA dollar starting from the root. We know that we are going to follow this path because it starts with X, and there's an A here, and there's a mismatch at this character. The third character of this edge label does not match. So we have a mismatch in the middle of an edge. So as the algorithm states that, we label this part, we break the string at this point after XA. We insert a new node here, an intermediate node, with the label XA from the root to that node, and the remaining part, BXA dollar. This was our first, and we do this, okay? We split the edge label like this, and we can safely add our mismatch part, which was dollar only, okay, as the new child to this intermediate node. Okay, because the first two characters are already matched. The mismatch part, the dollar part, is added as the new child to this node. So XA dollar is added like this. Now, the fifth suffix, A dollar, we do the same thing. We follow this path. We have a mismatch here in the middle of this edge. So we split that edge into two. BXA dollar, this was our second. And this dollar, again, was inserted here as the fifth. So A dollar is represented by this fifth leaf node. And the last suffix is dollar itself, the sixth suffix, and it's added like this. So this is our suffix tree, which is exactly the same as this tree. Okay, you may say, okay, oh, this tree is different. XA is here, but your rightmost leaf node is BXW. So actually, these are isomorphic trees. Okay, their visual drawing, their layout, the layout of the tree is irrelevant of the data it has. Okay, in terms of the data content of the tree, they are they are same trees. Okay. They are not even isomorphic, okay? They're actually, to talk about isomorphism, we should have different labels, different characters, node names should be different. This is actually a different layout of the same tree, okay? So this answers the question, this comment is to answer the last week's question, whether we have a unique tree for each sequence or not. If you use this algorithm, you're always going to get the same tree. This algorithm has because in no point, if you look at the algorithm, in no point of the algorithm, we need to decide, we have multiple decisions that we choose from. Okay, it's a deterministic algorithm with very fixed decisions. And thanks to the constraints on the suffix tree, we have a unique path from the root to a leaf node. So because of these reasons, there's always a unique tree for a given suffix for this using this algorithm. You may ask, if we use a different algorithm, can we have a different suffix tree? Probably not, but I haven't thought about this in detail. It may be a good exam question. Okay, so you should think about it. I mean, if I gave you a different algorithm to construct the suffix tree, could you have a different suffix tree for the same string? Or is there always a unique? Probably it can be proven. It can be proven that there's a unique suffix tree for a string. I'm starting to think about a proof by contradiction. It can be proven by contradiction that there are no multiple trees for a given string. But I leave it to you as an exercise. It will be nice to think about the details about suffix trees. This is another example construction. Very similar to our example with just a letter C at the end. Okay, so, and this is how the final suffix tree looks like. And now let's think about the complexity of this algorithm. This algorithm that we have just used, well, how much time it's going to take to construct the suffix tree, and what about space complexity? What is the space it requires? Okay, let's start with space, the easy one. Here, we have a tree, and we know that for a string of size, so in order to do this complexity analysis, this is our input. Our input is encoded as an input of length n, as a string of length n. So we have a string of length n. If you construct a suffix tree for it, how much space are you going to need? What we know here is that our tree is going to have n leaves. That's the exact number. We have n leaves, and each path to these leaves are going to be unique, And if we have, for example, if also, there's another parameter actually that is required for complexity analysis. This is the size of the alphabet. How many letters are we going to have in our alphabet? And this is alphabet size. Is, for example, let's also say it's M. Okay. So alphabet size M means that we have an M-ary tree. Any intermediate node may have at most M children. Okay, we cannot have more than M children because we do not allow different an edge, the children going out of a node to have start with the same characters. They cannot start, so they can have at most M children if we have M characters in our alphabet. Now, a node, a tree with N leaves actually it contains on the order of, I mean, if you have N leaves, you would have O(n) number of nodes regardless of this. You can consider this M as a constant. Okay, if you take this M into account, you can also have, you can say that it depends on M as well. But even if we have, let's think about it. If try to come up with the complexity with M also as a parameter, not considering as a constant. Okay, how this M affects your complexity. Another thing we should note here is not just the number of nodes in terms of space, the edge labels as well, right? You need to store the edge labels somewhere, and the edge labels. Each of them is a path from. There's a unique path from the root to a suffix. So in other words, the total length of edge labels actually can be easily found. We have a suffix of length 1. We have a suffix of length 2. We have a suffix of length 3. We have a suffix of length 4. We have a suffix of length m+1. Okay, so the total space that to store the edge labels is going to be equal to this one, right? Because I mean these are all, they all denote the length of the path from root to a particular suffix. They are different. So this is the suffix of length 1, and it goes to the suffix of length m+1. And obviously this is going to be on the order of n square. Okay, the series, the summation of these numbers from, it's going to be n times m+1 divided by 2. Actually, m+1 times m+2 divided by 2, which is, if you ignore the constants, it's going to be in big O notation, it's going to be n square. So by looking at this, we are going to need n square space. And what about the number of nodes? How many nodes are you going to have, can you have in a suffix tree for a string of size n and with alphabet length m? What is the number of, how many, for example, can you have n cube intermediate nodes? So let's start with, in such cases, I mean, when the general case is difficult to solve, in such complexity analysis, just start thinking from the simple case. Imagine that your alphabet contains only 2 characters, okay, in which we are going to have a binary tree, okay. So imagine we have a binary tree with n leaves. Okay, we have n leaves here. And imagine the worst case, that it was a full binary tree with n leaves, with all the intermediate nodes possible. I mean, every intermediate node has exactly 2 children. It's a completely balanced and full binary tree. That's when you can have the maximum number of nodes, right? I mean, you could have this, you could have something like this as well. I mean, for example, this one is directly, some of the leaf nodes may be directly connected to the root node, okay? It can be something like that. So you can have a tree like this, or you can have, in such case, if your tree is like this, you will have, if you have n number of leaves, you are going to have n such nodes to create this tree. So at most you can have 2n leaves in your tree. But let's consider the worst case in which this tree is a full, with all the intermediate nodes possible, a full, complete, balanced binary tree. Okay? So if you have n leaves, the question is, if you have n leaves in this binary tree, how many nodes, including the root, can you have, not can you have, do you have exactly in this balanced binary tree? So you need to work out some equations, some mathematics to do this. So for example, what is the depth of this tree? The first thing you need to work out is the depth of this tree. It's log n, right? If you have, it's a log n plus 1 or log n. If it depends on how you describe the depth of the tree. I mean, is this considered depth 1 or depth 0? It depends on that. This is called a depth 1 tree in regular notation, I guess. For example, if you have 4 nodes, log 4 is 2, so it's actually it's going to be, this is going, if you consider this level 1, level 2, level 3, so it's basically then log n plus 1, okay? But still, in terms of big O notation, it's order of log n, okay? That's the number of, that's the depth you are going to have, log n, and but how are you going to use it to find the number of nodes? What you can do is a binary tree of log n. How many nodes of depth log n? How many nodes can it have? You can consider that, and it's going to turn out to be, even in this case, this part is also order of n, right? Okay, if you have n leaves. This part is also going to be, you cannot have n square nodes. If you work out the math, you are going to see this one actually has exactly n leaves as well, or n divided by 2 leaves. I mean, I'm not sure about the exact mathematics here, but it's probably n leaves we are going to, n intermediate nodes, not leaves, n nodes here. So total, we are going to have 2n nodes. Which is, again, in big O notation, On. So the number of nodes, in terms of space complexity, the number of nodes is not a concern, actually. We are still linear. We need linear space in terms of the number of nodes. However, in terms of the edge labels, we need On square space just to store the edge labels. So this seems like a bottleneck. So what do we do? So we have On square complexity, and the main reason is that storing every edge labels in the tree separately, if we store everything, if for example, for a string like this, each suffix is, each label is stored separately. There is no sharing of labels. At the worst case, we are going to have these things. Actually, this analysis applies only when we have a string consisting of different characters like this. Because this analysis, this 1 plus 2 plus 3 plus 4, is not going to be the exact number of, count of letters that you are going to have in edge labels. Why? Because certain edge labels are shared between suffixes. Okay? For example, this XA, this edge label is shared between XAB, XA dollar, and XA dollar. So when you are going to count this as 3, for example, you should actually subtract this 2 from this. It's actually the cost for this suffix is going to be 1 because 2 of its letters are already covered by the other path. You don't store it twice. They are shared. So this ON square, the exact ON square, happens when we have a string like this with all different characters. And this is the space complexity ON square, and we can actually apply a very nice trick to reduce this ON square to ON. How we are going to do that? Any ideas? How can we reduce this? How can we store edge labels more efficiently? That's the question. So let's think about this. Do we really need to store the edge labels letter by letter? So where do they come from? Where do these edge labels come from? What? Yes, exactly. So that will be the solution. We only need, so all these edge labels, actually, they are coming from the same string of length n. And each of these edge labels is a substring of this. So we are storing actually our edge labels are substrings of this final string. And a substring can be indicated by 2 numbers. Beginning of the substring, ending of the beginning index and end index. So each edge label actually can be stored by using 2 numbers, these 2 indexes, which will, since you have, since the number of nodes is linear in terms of the length of the string, the number of edges are also linear. In a tree of n nodes, there are n minus 1 edges, because trees are acyclic, there are no cycles. So in a tree of n nodes, there are n minus 1 edges, which means that the number of edge labels you are going to be using are again going to be linear. If you're just using 2 numbers for each edge label, you are going to be wasting just linear space. So a suffix tree can be stored in linear space, in ON space, if you have a string of length n. And however, the running time complexity, we are not so lucky. By using this simple algorithm, we cannot reduce the running time of this algorithm to ON. For each suffix, we follow the path from the root to all the characters. Therefore, we spend this much time for each suffix, regardless of the edge labels. I mean, we need to, when we are following from the root, we check each character by character. We start from the first character of the suffix, and we do this character by character, and we spend this much time for each suffix. And at the end, the running time complexity of this algorithm becomes ON square. So it is a quadratic running time, but it can be stored efficiently in a linear space. Okay, so storing the labels efficiently, we can just use the indices instead of storing the exact label. We can just, this will reduce the space complexity to ON. And fortunately, people have worked out the running time complexity. There are alternative algorithms that we have discussed today, and they can construct the suffix tree in linear time. So there are linear time construction algorithms, which are more complex to describe. And there are certain variations of these trees which share certain edges, certain subtrees can be shared between suffixes. And this makes the algorithm more complex. But for the context of this course, just use this quadratic construction time algorithm and this space efficiency. That will be enough. And there are some applets on the web for suffix tree to show how suffix trees work. You can check those out. And this is one such example. Let's see if that link is still up. Yeah, it's still linked from France. Yeah, it's still working. It even has a source code. So where is it? Somehow, yeah, here. So you can just enter a text, for example. You can try XAB, XA. Okay. Let's see if it's going to put the dollar. Oh, also let me just. Yeah, but the string part is still small. Even if I zoom in, the applet is still like that. Oops. Anyway, so yeah, we can see our nodes really large. So this is our first string. A dollars, A, BXA dollars. This is BXA dollars. So you can, our suffix tree at the end looks like this. So you can try out this applet on your own if you want to learn more about suffixes, suffix trees. And we can use to use suffix trees for pattern matching. For a given, after we have this suffix tree built, we can query any pattern on this suffix tree and check whether this pattern occurs in our string or not. And for that, we actually use the same algorithm that when we are using during construction. So for your pattern of length m, you start searching your pattern from the root. You follow a path. And there's a unique path from the root because we know for sure that each edge label starts with a different letter. So you can follow a path by matching the characters of your pattern one by one. And if you can match all the characters of your pattern, if you stop at the beginning of a node or at the middle of an edge, if your pattern is a prefix of some other suffix, it means that you can match all the characters successfully. It means that your pattern exists. And the subtree, actually, from the point you stop, you are going to have a subtree below that stopping point. The number of leaves in that subtree actually gives you the number of occurrences of your pattern, how many times your pattern occurs. Your pattern may occur 100 times, for example, in a large string. The number of leaves in that subtree is going to give you the number of occurrences, number of all places where it occurs. And if you cannot successfully match your pattern, it means that your pattern does not exist in the tree. Okay. So all leaves below that matched stop point represents the occurrences of P, your pattern. Here in the XAB, XAC, let's search for XA. When we stop here, so the subtree at this point is this. So the first suffix and the fourth suffix are the suffixes that contain this pattern XA as the prefix. So XA occurs 2 times in our tree. We can understand by looking at how many leaves exist below this point. And the search time is OM plus K, where K is the number of occurrences of P and T. If you're just interested in the yes or no answer, whether your pattern occurs or not, it's just going to take OM time, if M is the length of your pattern. But if you're interested in all the occurrences, for example, if your pattern occurs 5 times, if you're interested in to find out all these 5 different places, it's going to take OM plus K time. You need to spend K time, additional K time to find that. Okay. And even for very large problems, even a linear time and space bound is not good enough. And sometimes we can use other variations of the suffix trees called suffix arrays to conserve memory. Suffix arrays are much more, even if it's linear, the constant terms, instead of this 2n, okay, the space complexity here is on, asymptotic complexity in big O notation is linear, but the actual complexity term is 2n, okay? You need, if you have a book of size 1, if you have a book of size 1 gigabyte, you are going to need 2 gigabytes for your suffix tree. So this is saving 1 gigabyte. I mean, even if sometimes these constants in this complexity terms may matter, so suffix arrays may be used for that to conserve more memory. But in terms of running time, suffix arrays are more costly compared to suffix trees. So before we start suffix arrays, are there any questions about suffix trees? Okay, no question. I'm going to skip this part, the alphabet size and generalization to multiple strings, meaning that creating these two topics that discuss how alphabet size affect the running time and or running time of pattern search, and how we can create a single suffix tree for multiple strings. And we do that for example, to solve the longest common substring problem. We can create a single suffix tree for our multiple strings at the same time. Given 5 strings, you create a suffix tree by concatenating one after another. And the longest common substring in these actually can be found by finding an intermediate node in which occurs in all these 5 strings. This is going to be the longest common substring in the. So I'm going to skip this alphabet size. And the generalized suffix trees, as I said, it's basically about constructing a suffix tree for all these strings by concatenating them. And the longest common substring problem can be solved by this generalized suffix tree by constructing a suffix tree like this by concatenating 2 strings S1 and S2. And marking every internal node of the tree with 1, 2, or 1, 2, depending on whether its path label is a substring of S1 or both of them, or just single S2. And finding an edge label with the largest string depth will give us the longest common substring of these two. Suffix trees also have been applied in practical applications like selecting oligonucleotide probes for microarrays. And here is a paper about use of suffix trees for this purpose. And let's see how am I doing on time. Actually, we have run out of time. I'm going to start suffix arrays tomorrow. In the first hour, we are going to finish suffix arrays, and we are then going to start the multiple analysis of multiple sequences, which are patterns and profiles. We are going to talk about them tomorrow. Okay, so that's it for today. See you tomorrow.